Welcome everyone. So this is our 71st live stream geometry. We have 3 people here with us today. One of them is new. And today I'm going to do a contest called Mathley. So I actually did this contest a while back on my channel, but I think I did it from the year 2012 before, whereas now I'm taking problems from the year 2015. And it's a certain Vietnamese math journal that has these problems, and a lot of them are like really elegant. In general, I really like the problems from Vietnam. So if you want to join our session in the future, feel free to email me at mgreenb801@gmail.com. It's in the description of my video, and we meet every Sunday at 8 a.m. US Central Time. All right, so with that, I'm going to share my screen. Hold on just a moment. All right, so here's the first problem from Mathley. It's kind of interesting. There's no circles in it, and it looks like kind of an easy problem, but let's see. So basically we have, so AD, BE, and CF are 3 segments whose midpoints are on a line L. So what I'm going to do, I'm going to have to rename a couple things. So I'm going to call this P, Q, and R. So these will be the midpoints. So P, Q, and R. And then I have A, B, and C. So this will be A. And then B, C, and then I reflect them. So, oh, whoops, I want to reflect across a point. So, this will be D, E, and F. All right. And then we draw the lines D, E, F, and BF. So first I'm going to draw these segments. And then we want to draw the lines. Maybe I'll change this a little bit. So it's more, it's a little less of an obtuse triangle, so maybe something like that. And I want to, so the points, so X, Y, and Z lie on these 3 lines. And those lines are all parallel to line PQR. So I'm going to draw that. But we need to see where these 3 lines intersect those lines. So I'm going to try to make the diagram a little better. So yeah, this question, there's no circles involved. It's all lines, but I still think it might be a little bit tricky. Yeah, this is still a pretty obtuse triangle. I want to make it more of like maybe if I can make it an acute triangle, let's see. So what if, actually that looks all right. I'm just going to shrink it a little bit. Okay, so basically we want to see where, oh, but line DF, we want to see where the line through A meets DF. So DF is still, let's see. I want to make this more so that I can see the intersection. Maybe like that. So well, this would be X. Is that right? No. Whoops. This should be X. And then, oh, I need to see where this line meets the F. Okay, that's what makes it tricky. All right, yeah, I think if I do this, that's maybe a little bit better. So I think it's like that's X, and then this is Y, and then this is Z. And I need to show that X, Y, and Z are collinear. Is that true? Let me make sure I did everything right. So let me check it. That's not right. Let's see. I want to draw the parallel through B. Oh, it's this point right here. Whoops. Okay. So this is X. This is Z. And then X, Y, and Z should be collinear. All right. So that's what we want to prove. Let me see if I can shrink the yeah, Z is on B. Let me see if I can shrink this a little bit and make it a little nicer. So yeah, DF, I want to make it a little more slanted. But it looks weird. I don't want A to be, so yeah, maybe I can make C a little farther away. I think that looks good. That looks like a good diagram. And now I'm going to hide a couple things, just because the lines are too long. Here's EFX, EDZ, and then FDY. And AX, CZ, and BY. All right. So we want to show X, Y, and Z are collinear. It's such a weird configuration because there's like no circles, but it still feels like it's kind of hard. So yeah, can we use Menelaus somehow? What if X, Y, and Z were collinear? By Menelaus, so we have like the ratios ED over EZ, EF over EX, and FD over FY. Is there a way to use Menelaus to show that? Yeah. All right. So I forgot, like, usually I use Menelaus in a different form, but do you know what the ratios have to be for EF over EX, CD over EZ? Do you know what the relationship has to be for X, Y, and Z to be collinear? ERIQ lemma? Oh, I think that might be something different. So it almost looks like AD and BE are parallel. So I'm just going to move this a little bit. But yeah, I don't think this is the ERIQ lemma, but I'm not sure. Or we could try Desargues' theorem. So yeah, is there any way we could use Desargues' theorem? Because showing these are collinear, basically all three of these parallel lines, they're like lines through a point at infinity, right? So we're basically what if I did it like this? So I have triangle ABC, and then what if I took the triangle through EF and the point at infinity? No, you can't really do that. So yeah, can we find the ratio EF over FX? That might be a good start. What if we use Desargues on triangles ABC and DEF? Actually, let me try something here. I wonder if CB, no. This is tricky. But yeah, all these parallels, I feel like it has to be something with projective geometry, like projecting. Maybe there's a way we can reframe this problem, like showing two cross ratios are equal. Yeah, I want to reframe it that way. What cross ratios would I want to show are equal? I'm going to draw this. I almost feel like I want to add this point right here. Yeah, what if I did this? So I'm gonna draw in a few points here. So what if I first let xz meet be at a point, and then I try to like calculate the cross ratio EGQH or something like that. And then I let YZ meet it at H prime, and I try to compute the same cross ratio, and then I try to show that they're the same. So yeah, for example, let's say I did this. So XZ meets BE at H. Can I calculate the some cross ratio here between these points? So if I draw all the different parallels, so they meet this line, let's see. All right, so we have conjoining. Let's see. That would be kind of interesting. So are the reflections of, thanks for joining, Con. Are the reflections of X, Y, Z across PQR collinear? So there's X across P, Y across Q, which is going to be far away, and Z across R. Oh, I can actually see them if I move the zoom thing away. No, I don't think so. Z across R. All right, so I'm going to undo that. But yeah, that's what I'd like to do. I'd like to draw in XZ and let it meet this at like a point H, and then like calculate some cross ratio. Let's see. Label that point. So what about like EIHJ? So if I draw, let's see. What do I project through? Yeah, I'm just not sure, yeah, what I should project through. Let's see. Let me see if there's another way we can think about this. Yeah, let me try using desargs again. So I mean, basically, these four lines basically concur at a point at infinity, right? So maybe, like if we have triangles ABC and XYZ, those we could basically apply desargs on that. So basically, let's try that. So let's draw a triangle ABC. And then we have that BY, CZ, and AX concur at the point at infinity. So from there, we should be able to get some collinearity. So basically that means if we take the intersection, oh, but that's trivial. Yeah, never mind. Well, actually, maybe not. It says the intersection of AB with XZ. Yeah, it's actually really hard to think about this because we know that they're collinear. But basically, if you take the intersection of AB with I think AB with YZ and BC with ZX and CA with XY, it says that those 3 points are collinear. All right, I'll spend like maybe 10 more minutes on this problem before we move on. But yeah, it's a hard one. Unless we figure out like a new idea. I feel like I want to extend some of these parallel lines. Let me draw the whole parallel lines. I feel like it could be helpful. I like let it intersect here or something. So yeah, I could try to show YH over HZ equals YI over IX. But let's see. So YH over YI, it's equal to BJ over BK. And HZ over IX. Do we have any other ratios? So yeah, I think I might be able to write like a whole bunch of ratios here. Okay, so YH over YI is BJ over BK, and then HZ over IX. Well, I know I could maybe try to find HC over IL, which is DL over LZ, and then I could try to find IL over IX. And for that, I might be able to use Menelaus, but yeah, this is just getting kind of complicated. Although maybe it's worth it. Maybe it'll work. So like, if I draw these points, oops, this is covering it up. So yeah, I want to calculate HZ over IX. And that's the same as HZ over IL times IX over IL. I can write that in terms of X to F over FE and ED over EDL. So IL, yeah, IL over IX is HZ over HM. Yeah, this is tricky. All right, let's try this for like 5 more minutes and then I'll move on to the next one. Yeah, we haven't yet used like that these are midpoints. So yeah, I think that's a key fact that we have to use somewhere. Let's see. So yeah, I want to show YH over HC is YI over IX. And then HC over IL, we can try to find that ratio. And then IL over IX. Like, is this just bashable? I feel like we're still missing something because, yeah, let me write it all out on paper. Let's see. L times IL over IX. And that's HM over IX. All right, let's move on to the next one and we can try to come back to this later. Seems pretty tricky. Let's see if I can find an easier one. So this one looked kind of interesting. So we have two circles and they're internally tangent to another circle. So let me call this O. And we have a point A, that's point B. And we have two circles that are internally tangent at A and B. So I'm going to draw the radii. And we don't know how big the circles are. So one could be a bigger circle and one's like a smaller circle maybe. And then we want to draw the tangents from A to that circle and the tangents from B to that circle. And we want to show that it makes like a cyclic quadrilateral. Okay. So basically it's saying, okay, actually, yeah, we want to see where those tangent lines intersect. So, so it's kind of like we have this point. L1 intersects T1 at X. Yeah, it doesn't. They don't tell you which one's T1 and which one's T2. But if it's these 2 points, that doesn't look cyclic. So I think they're probably the farther away points. So it's like, yeah, let me shrink this diagram a little bit. I want to be able to see this intersection point out there. Let's see. So if I make it kind of like a small circle like that, let's see, if that's X, I'm going to rename it in just a second. And then I would want to see, so here's the other tangent. Do they mean like this point? I think so. So wait. Is AFBE cyclic? No. I wonder what they mean. Let's see. Internally tangent. Did I do something wrong here? It seems almost like the problem's not true. Because if I draw this, I don't see any other point that passes through. Right? Doesn't this look, it looks like it's not true, right? Maybe they made some mistake. Let's see, I think maybe they put a picture. So here's the, let's see if anyone, no one responded to it. Okay, let me try a different, let me look at this for like 3 more minutes, see if I can figure it out, what they mean. Otherwise, I'm gonna move on to another one. It looks like it might be a circumscribed quadrilateral, like ABXY. Maybe they meant to say it's circumscribed. Let's see. Yeah, I think that's actually what they might have meant. Not that it's cyclic, but that it's a circumscribed quadrilateral. Yes, that's what it looks like. Okay. So yeah. I think that's the problem. So that's what I'm going to change it to. Okay, so we'll call this X and Y. Yeah, let me draw that let me just make sure it's true. I'm going to move A and B around. Yeah. Okay, so let me change the question. Prove that AXBY is a circumscribed quadrilateral. You guys think that's what they meant? I'm pretty sure it is, right? Let me draw these points. Okay. That, and then we have that. Yeah, yeah, tangential quadrilateral. Exactly. Yeah, so yeah, maybe we could show it by Pito's theorem. Shrink the diagram just a little bit and move some things around. So yeah, maybe we could show AX plus BY is AY plus BX. I wonder if the common tangent of these circles passes through Y. I don't think so. Yeah. So let me try to draw. So the incenter would actually be the intersection of AB and BC, right? Because AB is the bisector of XAB, and BC is the bisector of this. So really, we want to show that this point is the incenter. Let's try to draw that. Let's try to draw the incircle. So if I take the perpendicular, then basically it's saying this is, yeah. So we want to show that J is the incenter. It almost looks like these concur, but I don't think that's true. No, that's. So I guess another way we could say it is prove that angle YJ bisects angle AYB. That's another way to say it. I wonder if it's worth extending the tangent lines to meet the circle. So I'm going to try that. And that's LM NONP. And maybe I could even, extend BC and AB to meet the circle. Those almost look collinear, but they're not. Yeah, I'm going to hide this circle for now, just make the diagram a little easier. Yeah, maybe we could use Piot's theorem. So AX is AF minus FX. Let me try something. One sec, I'll be right back. All right. What if I draw the angle bisector? So let me see, if I draw this, basically I want to show it's the angle bisector. So yeah, I could maybe try to use the angle bisector theorem. Oh, do those concur on that circle? I don't think so, but it's, yeah. I'm going to go hide these segments. Actually, what was the purpose of drawing it? Oh yeah, I'm going to delete that. All right, looks like Constantinitis is joining us. Hey, Constantinitis, thanks for joining. So this is our second problem. This is a pretty hard session today. B must be the homothetic center of CJ, and A must be the homothetic center of JD. So is J the point circle at J? Oh, you mean, yeah, the circle that I hid. Okay. Yeah. So maybe there's some theorem if we have like two homotheties. I wonder what the homothetic center of these two circles is. That might be, so it's going to lie on line CB. Maybe we could use Monge's theorem. So, oh, but it would be, Monge's theorem would be trivial in this case. Is there anything special about this point? Maybe this point's collinear with A and B. Yeah, it looks like it. It looks like the line AB passes through the center of homothety. I don't know if that's trivial.
That's due to the Monge theorem.
Oh, it's true by Monge's theorem. Okay. So maybe that's helpful. I'm not sure. Yeah. So yeah, let me hide a bunch of stuff. Let me just draw the intersection of AB and CB. And then we know that that is the center of homothety. We call it S. Oh yeah, that's just trivially that's just Monge's theorem. All right, see you next time. Yeah, Jamin has to hop off. P toe. We have some nice length relations. So yeah, maybe P toe would work. Yeah, that's. Yeah, because we know AF is equal to AG. So maybe we could find something about AX and AY from that. Then we know BH equals BI. So that gives us something about BY and BX. Yeah, not sure where to go from there. Maybe this XF is the power, XF squared is the power of X with respect to this circle, and XI squared is power with respect to that circle. What if we consider two circles? We can show XF plus HY equals YG plus XI. So it's equivalent to that, or GEO king. Like you're saying the problem is equivalent to that, right? And then Constantinitis. So sorry if I mispronounced your name. One tangent to XB, XA, and YA. And prove they're the same circle. Yeah, so it's kind of like you're saying extend AN and BL and find the in circle, and then extend BM and show that the two in circles are the same, kind of. So yeah, I see what you're saying. So yeah, Constantinitis, he's basically saying like, we would draw the in circle of XAT, and then we'd extend those two, and we draw the in circle of that, and we want to show they're the same. So what I was thinking, so from what GEO King wrote, that's the same as showing that XF or XI minus XF equals YH minus YG. But XF squared is the power of X with respect to this circle, and XI squared is the power of X with respect to this one. So maybe we could use Casey's theorem, because that we might be able to get XI squared minus XF squared, and then factor it. Yeah, I'm not sure. All right. These problems today are, let's see, if I drew the tangents at A and B, A and B to the big circle. Let's see. like that. Is the tangents at x, y, let's see. No, those don't concur. Let me try. What about the tangents at some other points? So M and N. Let me try. Let's draw this point. See if there's anything interesting. So it looks like, oh, but yeah. Is AGHB cyclic? No. It's almost, but not quite. All right, 1 sec, I'll be right back, guys. All right. Let me check that the problem's actually ACDB is cyclic. Interesting. Wait, how can that be? Because C and D can move around. No, ACDB can't be cyclic. The C can basically be anywhere it wants, and same with D, anywhere on the line OA. Let me make sure that the problem's, so I'm pretty sure the problem's right, but I just want to make sure so we don't waste our time if it's not. (81.03), 81.03, yes. AI passes through the midpoint of arc BL. Interesting. Okay. So you're saying AI bisects angle BAL? And I guess similarly BF. So let's see, why is that? Homothency. at A. Okay, so homotheity at A, it takes I to T. Let's see. All right, I'm gonna delete these for now. That's a good observation though, that it passes through the midpoint. I'm gonna add those back in. Yeah, I don't think we need point S, so I'm gonna delete it for now. Well, actually, let me draw segment AB. So I'm still trying to understand. So homothety. So homothety at A, it takes point I to point P. Oh, because they're tangent. So it's true by symmetry, because basically, I think I see it. Oh, it's Archimedes' lemma. Okay. So, but I thought Archimedes' lemma says that if you take like the perpendicular from the midpoint to like a side, but like, isn't Archimedes' theorem like you take the perpendicular from T to BL or something like that? Okay, I think basically we want to show angle TAB is LAT, but LAT is LBT. So basically it's the same as showing that triangles TIB and TAB are similar. It's basically the same as saying that AB squared is AI times AT. Okay. I must just forgot it. Okay, so T is the midpoint of arc BL. So that means T is the, let's see. Ti times Ta equals Tb squared. Oh, okay, now I get it. So the tangent at I is parallel to the tangent at P, so it follows immediately. Okay. All right. Yeah, it's like a mixed linear. So yeah, maybe that's helpful. So basically, yeah, I think that is going to be pretty helpful because it says, but yeah, I feel like I need to draw the a couple end circles. So the end circle of BML, maybe. And the end circle of ANL. Whoops. Too many E's. So it's getting all messed up. So AS, so yeah, it's getting messy here, but yeah, I was trying to use the mixed to linear stuff. So AS passes through the midpoint of ML. Yeah, I think that, yeah, if you can see a way to use mixed to linear, let me know. But yeah, I don't want to draw it all because it's kind of messy. So yeah, maybe we could also draw AH. And that has to be the midpoint of arc BM, right? And then BG that's going to be the midpoint of arc AN. And then the question is, yeah, how does this help us show AX BY is circumscribed? Yeah, I think the last time we did Mathley, it was easy. It was like a lot easier, but it was a different year. So I think it got a lot harder in those 2 years. Is TIF tangent to ABT? Let's see. Oh, ABT is just a big circle. No, they're not tangent. Oh, ABC. Okay. No. So let's see. Can we use harmonic stuff? So we want to show that XJ is an angle bisector. Is that really true? I don't think XJ and S are actually collinear. No. But we want to show XJ is an angle bisector. Let's see. S is the just intersection of AH with the circle. Oh, okay. Sorry. This point out here. So yeah, that points the homophily center of the two smaller circles. Looks like Khan is rejoining. X. Sorry, is what equal to 90? Angle X. JXW. Oh, that would be really interesting if that were true. No, it's close. I wonder if these are perpendicular though, JX and CD. No, because then JY and CD should be perpendicular. All right, let's see if we can find an easier problem to work on. I want to solve a problem. Let's see if we can find something easier. This one looks easier. I think so. Let me see if there's something even better. This one looks easier. Okay, I'm going to go back just to see what Constantinides said. So the perpendicular through X and AB. Yeah, so you're trying to create a harmonic bundle, right? So you're saying, yeah, take this perpendicular, see where it meets AB, and then see if we can project it. I'm just going to look at this really quick, just in case it leads to something obvious. So yeah, does LP pass through that point? That's a good question. No, it misses it by a little bit. Let's see if anything else. QR. QR looks like it does pass through that. I think. Let's see. Oh no, QR doesn't pass through it. Thought it did, but it doesn't look like it. Let's try a little bit more. Just yes. I don't know. I doubt these concur. Yeah. All right, I'm going to move on to that other problem that looks easier, just so we could solve. I want to be able to solve at least one problem. So and these look pretty hard. All right. Oh, did you solve it? Oh, you're saying it's probably